This is Dr. Hakan Satiroglu. Today I'm introducing Week4 machine learning activity with using Penguin data. This session focuses on how Penguin data can be classified using machine learning, and it brings together 5 different algorithms: TLS, decision tree, random forest, KNN, and SVM. The aim is not only to run the model, but also understand how each one approach classification in its own way. A key goal of this session is to connect the technical side of machine learning with simple, practical explanation, rather than only showing codes, as you can see here. Simply, this is not teaching you any Python coding, but it's explaining some code inside. Then you can simply go and check or change those insights to practice or improve your knowledge. So one of the important points is in coding section, maybe you can say this test size is 70 to 30% here. Actually, it doesn't say test size is 30%. It means training side is 70%. So if you imagine data is one whole section of this figure, 70% of data up to here is used as a training data. After this section, 30% is used to test whether the model, the proposed model, is working well or not. I don't want to repeat precision at one macro level accuracy detail, because we gone through them last lecture. And these are the codes about machine learning. This mainly is used. If you ask me why is random state is 42, this is not like, it is going to keep it's going to keep the split reproducibility. In a way, maybe I can say the same code gives the same training and testing groups. Each time program run or machine learning is run, you are going to get this consistent result, because it's going to pick the same data for train and same data for test. This is important because you don't want to get some really boggling what was the earlier, which one is better, which data model used at some point, and why it is improved. So in a way, because we are testing the model is whether it's perfect or not. So therefore, it's important to use same data, and then maybe you can change that one in a way with multiply data set. Finally, you can, if you say, this is machine learning section, stratify equals y, which gives the class distribution balance across the training and testing sets. Since this is a Penguin classification task, it means the species proportions are preserved as much as possible in both parts of the data set. So overall, so you have many different species or classifications. Then this code stratify equals y is going to help you to train your data, train your model by choosing the equal as distributed, into the training data and test data. Okay, next slide. This slide is because I just add up from the Click, one of the Click tutorial. I find that one is really helpful, because main problem is that this machine learning. What was the main problem machine learning can solve? Which is Click is using AutoML. Okay. The key point is machine learning help organize and automate parts of machine learning process for different prediction tasks. In practice, these tasks usually falls into two broad categories: binary classification, multi-class classification, and regression. Binary classification and multi-classifications are under the categorical section, and one of them has got 2 options, other one is more than 2. Then regression is using the numerical values and estimating numerical values. I think that one is really important, the regression one. This is different than others, because the output is not a category but a number. The example on the slide is that expected lifetime value of a customer. In this case, the model predicts a real numerical value rather than assigning a label. like yes or no, or success or failure, or other categorical sections. Okay, so you can regression. So regression can be used when the goal is estimating quantity, amount, score, cost, or value. So machine learning is not just about one single tool for one single task. It means this slide is showing us one of the like horizon what you can run in by introducing machine learning tools. So overall, today at least I would like to capture partial least square, decision tree, random forest, k-means neighbors, and support vector machine today. But I think I'm not gonna reach at the end. I'm gonna make another one, another report for this for some of them. I don't know how much I'm gonna go through. So this slide is introduced partial least square at the beginning. We call PLS that one. In a classification setting, it is often adopted PLS DA. Yeah, sometimes they use that way. Okay. The main idea is PLS is the supervised dimension. Actually, all of these models are supervised dimensions and supervised machine learning elements. And so dimensions with PLS, dimension reduction can be conducted with PLS. So that means PLS reduces the number of variables, but unlike unsupervised methods, it does this while keeping the prediction target in mind. So it is not reducing elements without checking the prediction targets. So technically, PLS builds what are called latent components, which is, I'm going to jump to the next slide, latent components. So this is the PLS partial least square presentation. And these are new summary variables created from original predictors. So measurements such as body mass, Kuhlmann depth, flipper length, and other correlated predictors may overlap with each other. So it means you don't need to make your computer or your model tired. You can just redact some of the repeated things because they are correlated highly and they are explaining same things, and you don't need those variables. It means you can have smaller number of components, such as component one. And I mean, you are going to run various component groups, and you are going to check which one is more maximized relation to the target variable. In this example, target variable is okay. I didn't take that one. The species of the penguins, Adelie, Chinstrap, and Gento. We are going to practice on this data. That for this is like more than one category, not binary categorical, multi-categorical, multi-class categorical classifications exist here. And so you are going to creating components like the sum of the combination, and the outcome is more related with prediction value is going to keep. But if something is more repeating themselves, it is going to be reducted. So this makes PLS especially useful when predictors are numerous. If you have plenty of predictors, body mass, Kuhlmann depth, flipper length, these are called as a feature in click. Sometimes I call them variable because this is the part of the function. But in a way, these are the predicting of y is going to be, if it is too much, then if they are highly correlated, if they are unstable, then PLS is going to work. It's going to help on your analysis. In a data set like penguins, several body measurements may move together. So using them directly can sometimes create redundancy. PLS helps manage that by compressing the feature space into a simpler or more informative way of structure. If I need to say is a simple way or a useful simple explanation, if I have to use, PLS creates smarter summary variables, and keeping smarter variables, it doesn't just reduce the data for convenience, it reduces the data in a way that keeps asking what is most relevant for prediction. That is the main difference from PCA you may see, which I'm not gonna go through today here. main difference between PSCA and PLS. Overall, PLS compresses the feature space, but it doesn't. It does so with predictive purpose. It does keeping in mind its predictive purpose. It is not just reducing something important for prediction. Okay, so it is just keep checking. How you can run that one? I created this table, like the number of component, single component, and you are going to check the accuracy of that model, and macro level recall and loss errors. You are going to make this table, and you are going to pick the best convenient model for yourself. Yes, this is the part of that one, part of the PLS, and what you can do, you can run the codes more than one. You have to do actually. For example, you are going to run PLS component 1, maybe with only Kuhlmann depth, Kuhlmann length, then Kuhlmann length, flipper length, then body mass. Then you are going to check which one is better. And you are going to add only 2. It means 2 times 4 combinations. So you are going to run 8 times for 2 components. So that you are going to check that accuracy level, and you are going to improve you are going to pick the best combinational components to run your prediction. Then you can start to jump other machine learning, because you just made a redundancy of your unnecessary data or variables. So some of the PLS codes I have here. It means you are going to run more than one. Then you are going to fill this table, and you are going to check. You are going to pick the best parsimonious component group out of this table. Okay, let's run that one with by using our data set. Let's stop sharing that one. Call up screen. We are using that one. New codes. Because we didn't download terminal, Python terminal, but this collab screen is working and it's free, and it's really convenient for all of us. Same thing change in. It's going to work. It's didn't work. Let's follow. And I run this one. That to work. Running, I'm using some random disk in the computer. Choose the data sets. Oops. As you can see, accuracy level is run. And as you can see, 1, 2, 3, 4 components inside this model. Then you are going to create a combination of many different components. Okay, therefore, you need to run this program more than one, and you are going to get the best combination out of those ones. So yeah, then you are going to make this figure I made earlier, 91. 0.912, 0.88, 0.98, 0.62. Yeah. So you are going to pick when you finish this table, you are going to pick the best possible accurate component. It means you are going to reduce, if something is, let's say, 3 components, is more parsimonious. For example, accuracy is better, macro level is better, 89. Then you don't need to run 4 components model. Okay, so this is what PLS doing for us. Okay, now we can start decision tree. So this is the PLS coding, and The purpose here is to show PLS classification workflow is implemented for the Penguin dataset. So it means, this program is going and picking the dataset. As you earlier see, I pick here from my hard disk. You can automate that one, which I don't want to, because I want to things in my control, because otherwise it's difficult to explain in the lecture notes. So in that sense, this code is picking the Kuhlmann depth, length, Lipper length, and body mass. And the target variable is species. Species are about Adelie, Chinstrap, and Gento. That means this classification task is not regression. It means a multi-class level task. And if you see that, if you see that 130%, 42, and stratify Y, I already explained today, they are supporting reproducibility and fair evaluation in terms of different component groups, how it's going to work. And so this stage is not only running a model, but also about making a validation. So you need to create a kind of valid process, reliable process when you are comparing different groups. Yeah, I think this is the explanation I need to give you here. Also, I don't need to repeat. The codes are here for regression, PLS regression. Codes are embedded somewhere here. Let me find that one. The PLS model, predict test. Okay. Now we can start a decision tree. And this slide introduces the decision tree model. A decision tree is one of the most intuitive machine learning methods because it works by repeatedly splitting the data into the small groups, using simple yes or no answers, yes or no rules. Yeah, instead of trying to solve the whole classification problem at once, it breaks the task into the sequence of smaller decisions. By asking simple questions, Kuhlmann depth is greater than 17 millimeters, yes or no. Then it is jumping the next section, and it's asking yes or no for the next section as well. Same question and answers, yes or no. Then it is finding something, is keep asking itself at the beginning whether the aim is fulfilled or not. If this program is running, whether species is Adelie or not. So it is not included tree classification on this model. Trying to reach that one. Okay. Then when you ask as many as questions, as you can see, it is depthness, our classification depthness is created. Also, there is some kind of sample size. When you reach one point, you can reach maybe only your data showing only 4 lines is responding to this line. What does it mean, this line? If you're asking question and getting no, then another no, then when you reach that point, only 4 of lines are answering to Adelie, responding to Adelie. So it means that way. So sample size, how many of them? And this is one of the criteria we are running in the decision tree in programming. And this makes the decision tree easy to explain because its logic can be read almost like a flowchart. In many machine learning tools, we can see they are like a black box. We don't see what mentality they are using, like neural network. We really struggle to understand which points, which dots are making mistakes because we know hallucinations are existing in AI and machine learning, and we know, but we don't know which neural dot is creating that one. For example, this is one of the examples. So, but if you go with the decision tree, you can see the mentality, the logic of flow really clearly. So that's why it's really helpful to understand what is the machine learning. It's a good start. So each answer moves to observation down one branch, and the final lead gives the predicted class or sometimes class probabilities. It's up to how you are going to go, but you don't need to learn all of them because you need to learn only the main mentality of that machine learning, because it is not your task, because we are not like programmer, okay? And that is why decision trees are often useful, because it is clear when interpretability matters. If the interpretability is important by you, then you should go with decision tree, because it is the reasoning path can be followed usually. The code section here on the bottom here on the black section, I just make a screenshot from the Terminator. The code section represents the practical side of this process. The model is created by setting parameters as splitting criterion, the maximum depth, and the minimum number of samples required for splitting. So it means, as you can see, how many lines they are going to move. 1, 2, 3, 4. You can go as many as possible. So, but it does matter how many sample size are generated within that section. So after the model is trained on the training data, so because this code is not split data into 70 to 30, it's highly likely it's going to accuracy is going to be 100%, because if you don't split training and test data, it is training itself from whole data, it tests itself on whole data. It means model is going to work perfectly. So this is one of the missing part. If you are running these codes from my node, please make sure you split that data later. Okay, you need to add that section in this code in the terminal. Okay. So the code and the diagram are showing the same idea in two forms. One is from programming logic. So one of the program, other one is like a visual decision path. And the key teaching I can say here is key learning. I can say that decision tree acts like a rule book and turning measurement into the sequence of small choices that lead to final decision. One of the artifact illustration I have for this machine learning algorithm, let's split those things. I need to stop showing. I generated for you this one to run together, and you can see like interactive perspective. Some codes at the bottom as well. As earlier I said, this code is missing test and training data. Please, if you want to use at that section. Maybe we should start from exploration of the data. So this is interactive artifact, and it's designed to explain how decision tree works using Palmer Penguin dataset. I share the link earlier in my Week1 notes or Week3 notes, the dataset link. You can reach that data. The idea is to move from exploration to model building to prediction, and then the key concept behind the model, how it works. So rather than treating the decision tree as a black box, this artifact interactive exploration screen helping us to see what is it, how model is working, what decision tree is making for or standing for. The first screen is exploration of the data. So you can see the data set visually, and it shows that penguin species here, different penguin species with different colors. And probably you can use this scatter plot by changing these variables, and you can start to familiarize with your data. This method, because a decision tree tree can only split effectively if the features contain useful patterns. So I can say, this is useful pattern because the body mass and flipperland is good. And also I can say before picking up this data set, I made some homework, and I think that one is really helpful to explain this kind of training. As you can see, fulminant and depthness is just this, separating different species with clearly. And if you go with the flipperland, it's another way around. So greens are at the bottom here. If you change that one with body mass, greens are button, but blues and reds are mixed in each other. So kind of like it's really helpful data set to run this machine learning. So let's jump to decision tree. Decision tree as a second segment. This section is showing how the model turns those measurements into the sequence yes or no rules. Here's the you can adjust hypermeters such as maximum depth criterion and minimum sample split. And kind of criterion is another one, Gini and entropy. I didn't mention earlier that one. But simply all of them is the entropy and Gini almost same result you can get. But depthness and sample split is really important. Let's say if you put sampling here is, can you see 4 in red? Machine learning algorithm doesn't include that one here because it's less than minimum sample size. Okay, let's have a look. For example, 52 here. I'm not sure I can reach 52. I didn't include 52. This maximum 20. Okay, let's try it for this one, 13. If we make that one 13, 14. So as you can see, they are excluded. Okay, so these data is like this algorithm is taken out if you include, for example, only 2. It's going to include almost everything. So, and depthness is, I think you can see 1, 2, 3, 4 lines of depthness here. If you want 1, 2, 3 lines of depthness. So literally, as soon as you run, you change interactively, you can see how the algorithm, how the logic is going through in this model. And you can run your program according to that depthness and sample size and leaf sample size as well. I think I didn't include that leaf sample size here. Maybe I can improve that one as a section. So let's jump to the next screen. Oh, one more thing. I think I missed that one. 96% of the estimate accuracy. So this screen is this interactive screen is also estimating the accuracy level. That is important because it connects 3 levels of understanding at the same time. Visual 3, the model performance, and coding. 3 of them are here is presented. But don't forget, this model is run as a 80% training, 20% for testing. So if you change that one with different model, 30 to 70, you can get a different accuracy level. Also, don't forget some of the random states from 42, remember? That one is keeping the same sample size, sample groups or elements when you are running to make a reliable outcome between 2 models. So, these are showing the importance of the flipper length, 38%, Kuhlmann 28 and 24%. As soon as you just change your model, as you can see, the levels are keep changing. So as you mentioned, because it's automatically calculating the outcome. If I make that one on 1, 0 or 1, estimate accuracy 72, only flipper length is run because it is run by the flipper length. Okay, if you include 2, here is Kuhlmann length, then it's here included as a Kuhlmann length. Then Kuhlmann depth, because there are 2 different questions here. So the features, 1, 2, 3 features included. Okay, so yeah. So third section, third screen is that predict the penguin makes the model more concrete. So the aim of this model is about Adali is or about this categorical, because I run this artifact interactive model by using 3 different outcome multi-categorical classification. Adala is 67% with confidence. It is Adala. So Chinstrap is 33% and 0% is the Gentoo by using these elements, and flipper length is smaller than 2.205. So measurements can be adjusted manually here. I can adjust here if I touch, and you will see that this model is going to change. It means the questions we are using here could be, how we decide is 43.4. It means you can change those questions accordingly. However, you don't need to do, because decision tree is making that one is the best algorithm and with using nearest approach, and it is picking really a logical way. And it is the decision tree algorithm is doing that job for us. And so this screen is showing the confidence of the Adela is 67% decision tree model running perfectly, but we have still 33% is fault. So therefore, it's a bit still we have some gap to improve, isn't it? So we need to reach maybe 90%, maybe over 80%, and we can say something good. So some of the key features I add up here as a fourth screen. This screen is explaining the main parameters and the idea behind the decision tree in a simple term. And also it is following actually the Python codes. The criterion section explain how the tree judges the quality of a split using gene impurity or entropy. There are two different types. And the max depth section explain how many layers of questions the tree is allowed to ask. So this is the depthness. And sample splits. This section explains how many observations are needed before a node is allowed to split again to another question. So the samples leaf is section is explaining the minimum number of the observations that must remain in a leaf, in a final leaf. So together, these settings control all the balance of that decision tree. You can adjust and you can change. You can try to find the best accurate model. Also, the feature importance, that one is important screen is especially useful when it explains what the tree used most during the training. In this penguin classifier, we use flipper length appears as the strongest features because gentoo penguins tend to have distinctly longer flippers, therefore happen. Okay. Let's see. Flipper lengths. Okay, all of them. Okay. So as you can see, gentoo model, gentoo has got longer. They tend to be longer. Chipstrap has got some outliers there, but mainly its average is out there. Okay. So so this helps to connect biological meanings with machine learning logic. So the model is not choosing the features randomly. It is identifying which measurements reduces uncertainty most effectively across the tree. So this is the main point. And it takes time to grasp. You need to familiarize with data first of all. And you need to start to run different machine learning tools and with different components, maybe with PLS. Then you are going to start to understand the data itself better. So in that sense, this is the artifact. The interactive artifact is valuable because it's combined exploration, model training, interpretation, and prediction in one place. It starts with raw penguin measurement, turns into the decision rules, maybe tests how well those rules perform, then allows us to experiment with new values. In a sense, these presentations are giving us the business analytics elements as well, how we present our data. I hope they are going to be helpful for you as well. And I think we are going to jump to the next slide. Okay, random forest. After looking at a single decision tree, and it might have many different alternatives, but this is like a kind of process you need to do because this is not unsupervised machine learning. This is supervised decision machine learning algorithms. we need to improve. We need to find the best latent machine learning algorithm by using different alternatives. And so random forest, what random forest is doing is, if one tree is not stable enough on its own, a decision tree is easy to understand because it follows a clear sequence of rules, but that simplicity can also our weakness. So small changes in the training data can sometimes produce a different tree, different accuracy, different outcome. So random forest is coming from that point, is building a combination of many decision trees instead of relying only one tree. So therefore, it is forest. Okay. So in this slide, I just assembled methods like try to illustrate more than one tree, and it's voting the best majority and predict highly likely what is going to happen. So many decision trees and combines their outcomes are the subject of random forest. Each tree is trained, okay, on a slightly different version of training data, created through bootstrapping sampling. We have a new instruction now, bootstrapping. Like, you is just iteratively running that model maybe 100 times by picking with many different sections of our data, and it is just bringing us the best possible outcome. So you can think that way. Bootstrap is iterative way because we need to pick many different data group from our data, and we need to check whether they are parsimonious or not. In other words, the model repeatedly sample from the training data with many different various replacements. So each tree sees a slightly different data set and getting different outcome. Second important difference is here. Each split doesn't consider every feature. Instead, random forest uses only random subset of features at each step. This adds more variation across the trees, which is useful because it prevents all trees from becoming too similar or uniform background. So each tree develops its own view of the data based on both different sample rows and different sample features. Then the final prediction made by majority voids. So in the diagram in the figure I'm showing, each tree gives its own void, and the class with the most voids becomes the final prediction. This is why random forest is often more stable than single decision tree. One tree may more poor split or overreact to noise or something like it is not equally distributed data, and it means it's going to create noise. But when many trees void together, the overall model tends to be more robust and less sensitive to random variation in the data in our algorithms. So this is like a random tree is decision tree is an expert making a judgment and showing a really clear idea and logic. But random forest is a panel of experts voting and getting the best outcome from the single decision trees. So each tree sees the data a little differently, and the most common answer wins. So this is the like democracy, I can say. Okay. I think I have. I'm going to stop this one. I'm going to share that interactive illustration for this artifact illustration for this one as well. So random forests. I didn't include here, as I did in the decision tree selection, all different species. I made this kind of simple Kuhlmann depth and Flipperland, and many different trees exist, and forecast accuracy for different trees. Then we are reaching and voting the best tree, best outcome out of these many multiply round decision trees. I think after introducing single decision tree, this artifact shows the next step, how classification becomes more stable when many trees work together. A decision tree is clear and interpretable, but one tree on its own can be sensitive to small change training. So I think you understand that one. And so in the first screen, as you can see, exploration of the data, we have 342 observations, and 151 is Adelaide, Chisrop is 62, Gento is 123. So scatter plot is showing Clipper land and Pullman land, like for a scattered plot that one. And on the right, the single tree of the accuracy chart makes an important point. One tree may score 72%. Other one is maybe 79, 83, even 96%, depending on how the decision tree is built. And that variation explains why one tree is often not enough. The line chart is showing that shows that the forest affects very clearly. As the number of trees increase, accuracy rises quickly. But we don't need to go something extreme. We need to keep ourselves in an optimal level. As you can see, reaching very high performance by 20 to 30%. So the second, I think that one is done. Second one is this one, Forest Builder. That one is going to explain us somehow some coding, also some parameter interactively we can change, and we can see the accuracy level is changed or not. Some of the new terms exist here, OOB. Yeah, let's start from the beginning. Forest line is built 33 trees. And maximum length depthness is 4. And as you can see, Python codes, you can choose. You can classify your random forest classifier here as a model. Then estimator 33 trees. Why we have 33? Because as you can see, how many trees you are going to make is important to get the accuracy. Okay. So in that sense, an estimator 33, you can reduce that one. I don't want to change at the moment. Later, I'm going to change. So the accuracy is 96%, which shows this ensemble the performing strongly. It's not bad. The panel also maximum features square root here. It means 2 out of 4 available predictors are considered at each split. This selection might be important because it forces the trees to be different from one another. Trying to run these models, 3, 1, 2, 3, 4, 6, different models, 33 models, differently. And so this is the mentality, is you are using different models. So if you choose logarithmic way, it is going to change the prediction different way. But accuracy is not too much changing, as you can see. So only change it and change it. So yeah, this is inside the coding, inside the algorithm, how it works. The feature importance, maximum feature, the important bar, flipper length as the strongest predictors at the 40% at the moment, followed by the Kuhlmann length, 32%, Kuhlmann depth at 22%, and the body mass 6% at the moment. So even though the forest uses many trees, it still tells a clear story about which measures matter most. I hope it is clear now. It is like you need to include these two. You need to run your machine learning about these, and you don't need to go with body mass. Okay. So also this screen says it has got a bootstrap. Okay. Bootstrapping is sampling also random state here. Okay, why is it 42? It's interesting. Let's start with bootstrapping. The drop down in the drop down menu in this combo box, meaning no replacements are being used in particular rules, but the code panel underneath reminds us the OOB score is only proper or available when bootstrap is true. So this artifact is useful because it is not only shows setting, but also encourage careful reading of what each setting actually enables. Let's change with true. So Bootstrap just made everything included in the data. If you say no, it's simply splitting data 80 to 20%. 80% is for training, 20% for testing, and accuracy is in the by accuracy on the model. The model is learned from the training data and tested data later on. Its accuracy is 96%. I think I'm going to jump here or B, because out of back score is the pre-accuracy estimate. No separate test is set needed. Each tree only sees 63% of data, so the remaining 37 out of samples. So it means trees used many different lines, but 33% not included. So you can say 33% of the data is vested at the moment. So in your code, you need to write that one or b underscore score equals true, then leave 1 out of cross validation. So it's going to affect your or B score. This is random forest mentality, and it's important. 71% at the moment. If I say true, 86%, it's included more because we train everything included. Okay, Bootstrap is doing that job. This is how it is trained. It's important. Also, you can change that split, sample split and sample leave. In order to make decision, the leave samples should be 5. In order to split the sample, it should be each of the last line should be 9. So as you can see, I'm moving, and this is changing here as well. So okay, let's make one logarithmic. Logarithmic didn't maximum feature didn't make too much difference. On the maximum, no randomness. If random is accurate, it is becoming a lot of change. But in terms of feature importance, here, it doesn't make too much difference. Okay. This is kind of illustration, and maybe we can go to next voting screen, because that one is in my slide. It was there as well. This is the heart of the random forest. And here one penguin is passed through 15 trees. 15 trees. With the clipper length at 195 millimeters. Culmin length is 45 millimeters. And culmin depth is 70 millimeters. This tree feature, just three penguins are identified in the trained and tested data as Adelaide. And chipstrap is 12. Prediction is chinstrap is 80% of the trees agree. As you can see, that one is the algorithm is generating for your outcome, or the likelihood of being according to this criteria, which penguin is going to be in your prediction. This screen is, I think, helpful to catch, because it connects model to concrete example rather than I'm just only speaking codes and theory. It shows how set of measurement turn into this class of prediction. This is coming 80% is on the second section. But before going that on, if I change that one, you will see how trees are changing. You see that greens are coming. And flipper length is 260 millimeters. Culmin depth is same with that. If the flipper lengths are becoming longer, it means, can you see chinstrap and gento is becoming more likely. If I reach to up, it doesn't make too much difference. Chinstraps are 87%. So it is giving us the result as well. Yeah. Okay. The next section is I made that one is again, you can change and you can see the result, prediction result. However, these two screens same, but only difference. This one showing the trees outcome. What tree one is waiting for chip swap, tree two waiting for chip swap in this red color, Adelaide for blue, and prediction is void that trees are not I mean, displayed here. In this slide, I mean, in this presentation, I illustrated the n estimators. As you can see, remember the n estimators are about the number of tree you need to include. You can include. You don't need to make maximum. You should come to point something is middle into like, because as according to our, it was about between 20 to 30 was best. So I'm just gonna keep it to 20. 20. Then this one is according to this criterion. It's showing the chip swap is likelihood to 75% or 23s are agreed that chip swap is the prediction of this criterion question. But if you take it down, Gentoo is going to be more sensibly because the Gentoo is like a biologically longer Clipper length. So therefore, we know from our explorative data analysis, we see that one in this decision tree model. We know that one. Yeah. In that sense, a little bit key concepts in terms of how we are going to model. N estimators, I don't need to repeat that one. I think we gone down more than it needed. Bootstrapping is worth to mention. Bootstrapping is the idea of this random forest, and each tree is trained on bootstrap sample drawn with replacement and with the sample size as the original data set. Because of that sampling process, about 37% of the rows are typically not used by any one tree. Those unused rows becomes out of bag samples. Overall, this artifact is helpful to understand random forest mentality, and you can play and you can try to understand what is affecting what. And yeah, there are 15 trees here illustrated. You can make maybe more than this in your analysis. Yeah, I think I'm done because I don't want to keep longer my presentations. We will carry on with support vector machine and nearest neighbor models on our next lecture or tutorial. Thank you very much for listening.